Okay, so good afternoon. So I'll chair the afternoon session, this session. So our first speaker is Debraj from ICTP, and he's going to give a talk on quantum unitary evolution. So the time is 17 minutes, so it starts.
Okay. Thanks, Shamik, and thank you to the organizers for giving me this opportunity to talk to you people here. So as you can see, today I'm going to talk about this unitary evolution in quantum system, and then we will try to perturb the system with some non-unitary interactions at random times. So this is the idea. So first thing first, you know that, okay, if I have an isolated quantum system, evolution is unitary, and then we have coherent evolution, everything is like essential information are preserved. But in reality, perfect isolation is not possible, we know. So there are external effects that would come to your evolution. So typically, I mean, it can come from the environment or some measuring apparatus. So in this cartoon, you see that I prepared a system, and then I let it evolve, and then it is subject to like this non-unitary evolution, and at some point I will detect. So this is the general scenario here, and the interaction typically kicks in at random times, right? So what we want to study, exactly the same thing. So we will have unitary evolution, and then we will have non-unitary interaction at random times. So here, this random times, this is like classical randomness, and whether in quantum evolution, we have quantum randomness. So basically what we want to see, the main question, so what is this interplay between classical and quantum randomness? What are the consequences, okay? So just to start with, just think of any generic Hamiltonian of your system. And I am talking about one, let's say I choose one interaction operator T. So I'm not telling now, so what is this interaction operator? Just think that there is an interaction operator. So I start my system. So here I show two different realizations. Okay. So I start my system here. I let the system evolve for a certain time unitarily, and then I use this operator here. Okay. Then again I let the system evolve, and then again I use the interaction operator here. So these operators are like non-unitary operators in general. So and then I am interested what is the state of the system at a later time t. Now in different realization, the time gaps between two interactions, so these are taken from a random distribution. So if you consider different realizations for the evolution until time t, you will have different number of interactions. So for example, this is another realization, and we want to understand what is the average effect if I average over all the possible realizations. Okay, so this is the setting. Okay, so again, so you consider a typical realization. Let's say I say realization 1. So I start from here. So this is my rho 0 initial density operator. I let it evolve. Now you see I have this Liouvillean operator here that acts on rho, which is given by this. And then I have this interaction operator. And then I do the unitary evolution according to the Liouville operator from T1 to T2, and I do like this again and again and again. Now the question is, okay, what is the average density operator? Okay, so so this is for one realization, I need to take an average over the realizations. So first thing first, when I come here, I see that I need an interaction at time t1. So what is the probability that I will find a random number? And it comes from this distribution. So that's why I have this probability of like at what time I will get this interaction here. And then again I have this interaction operator, I do the same evolution once again, and again then I ask what is the probability that I will do an interaction at a later time, like which is t1 minus t2. And suppose in this realization I have p number of non-unitary interactions. So then I ask, okay, so this is the last time when I have this interaction, and then I ask, okay, from Tp minus to T, so here I do not have any interaction. Okay, so this is the general thing. Now to consider the averaging, I need to average over all possible this T1, T2, up to Tp here, where I do here, and again, in each realization, the number of non-unitary interactions are different, so I also need to do a sum over the number of realizations which I do it here. So this is the average density operator, where here you have the density operator at the initial time. Okay. Now, if I consider the whole operator here, so it's like I have rho 0, and then I have some operator ut, and I get the average operator. So this is like a super operator that acts on my density operator here and give me this average quantity. Now, if you see the formula, it looks very complicated thing, right? So it's very intimidating. But if you look carefully, you will see that there is a structure of convolution here. So you see that you have T1, so this is T1, and then you have T2 minus T1, and then you are integrating over T1. So this is a series of convolutions. And we know, I mean, when we see this kind of convolution, what we need to do, we go to the Laplace space, and we use this Laplace transform of convolutions, and you can write in Laplace space this complicated expression in a very nice way. You see, this is here. So in Laplace space, this is your rho 0, and this is rho 0, and this is the evolution equation in the Laplace space, where u tilde s is the evolution operator, which is given by this, where this L, this depend. I mean, it says that you have to take the Laplace transform here. And notice one thing. Now, what we have? So we have initial rho 0. We have the density operator in Laplace space. On the right hand side, so we have US, but what are the things, like what are the inputs here that we have? We have the Liouvillean, so we have the Hamiltonian here, so we have the interaction operator T, which I have not fixed yet, so T appears here, and also the distribution of time gaps. So we have three things. So far, everything is quite general. I have not specified anything. Okay, so now let's start to specify things. To make my life easy, I choose an exponential distribution here for PT. And if you choose an exponential distribution for PT, so this is like this, and then you know this Ft, you put it here, you can find what is this u tilde s in the evolution operator, super operator in Laplace space. So it has a structure of series, and if you expand the series, so it's like you have one interaction, two interactions, three interactions, and it goes on. The first term, which tells you, okay, there is no interaction, which is given by this. Now there are two things I need to specify. I have already specified PT, now I need to specify Hamiltonian and T. Let's specify the Hamiltonian. Now, to specify the Hamiltonian, what I will do, I will just apply my theoretical formalism to tight binding model. Okay? So, what is tight binding model? So it's like you have a quantum particle, let's say on 1D, and because of this quantum fluctuation, it goes like undergoes tunneling from nearest neighbor sites. So this is the Hamiltonian, where n is your one-year state. Now you can ask, if I start from some site n0, what is the probability distribution? So this is a very simple model. You can find the solution, and it is given by Bessel J function, like this way, J square. So here in this plot, I am showing the typical probability distribution, like the site occupation probability. So M is your lattice sites, and these are like with time you see that the probability, it goes like spreading over the lattice, and the average displacement from n0 is 0 here, and if you compute the mean square displacement, it is delta square t square by over 2. Now we have specified my Hamiltonian. Now let's talk about what is the interaction operator T. Okay. So what we do, we will take two scenarios. So I will consider projective measurements. Because today we have seen projective measurement. I mean in previous talk in the morning session, and then I will talk about stochastic resets. Okay. So what do I mean by projective measurements here? Suppose I prepare my system here. So at time t, it's a delta function. It starts to evolve, and then I do a projective measurement on the initial state. So I consider from this wave function, so the successive evolution is only from this part of the wave function. So I project to the state, and I consider the evolution from this part. And then again, I start from here, and I let the system evolve. And then again, I project on the same state, like initial state. So that's why the wave function is that I would consider for the next evolution, it is here. Now this is projective measurement is not new in quantum like systems. I mean, there are a lot of works. Abhishek has worked on this thing, this projective measurements quite a lot. For example, I mean, in their paper, they consider leftover component. For example, what do I mean by leftover? So you start from a system, you project, and the successive evolution are from the leftover component. Like you have this, if P is your projection operator, so the next successive evolution is from this 1 minus P. So what is left over after projection? And but here, what in our work, what we will consider the projected component. So we project, and then the successive evolution is again from the projected state, not from the leftover state. That's why we have 1 minus P here, but here we have P. Okay. Okay, so what we do, we start from some state, like some site N0, and we perform projective measurements at the same site N0 at random times from the exponential distribution. We have this formalism, we have fixed PT, we have fixed our Hamiltonian, and I am also fixed my interaction operator T, and you can do the calculation, analytical calculation, and you can show that here you will get, because in the limit lambda goes to infinity, that means you are doing repeated projections, so you will get the Zeno case, like the Zeno limit. So what we get is that the initial state over the time, so it decays like this. So this is like a comparable separation that you see in Zeno effect. But here what we are doing is that, so remember in Zeno effect that you need to project at regular intervals. So here we are not doing projection at regular intervals, we are doing at random times but repeatedly. So it's easier to implement if you want to implement in experiment. Let's come to the second part. So where I consider the stochastic resetting. So what we do here, we start from the initial state, we let the system evolve, and then the projection operator is such that we reset the system to the initial state. Now you can see this time, because I am resetting the system to the initial state, so there is no leakage. So that's why in the previous case, you see the wave function was going down, down, down. But here, so whenever I reset the thing, I start again from a delta function. So there is no leakage in the probability in this case. Again, stochastic resetting is not a new thing. I mean, maybe you know a lot about this thing. I mean, from this paper from Evans and Majumdar in 2011 in the classical in classical systems. Also in quantum systems, I mean, there are a lot of works here. I mean, in quantum system, I mean, you would have heard about heating times and monitored system, this kind of thing. Okay, so what we do again, so in our case, we have this whole machinery. We do the thing and we obtain exact results. What we see again, because of the resetting, in the tight binding system, you see that there was this spreading of the probability. So it's like you have this inherent delocalization. But now, because you are resetting your state at random times, what you see in the so you will see that the mean square displacement, now it will go to a finite value. So it will saturate to a finite value. So if you go to the stationary state in this case, what you will see that there is a time independent probability. I mean, there is no evolution, and that means that you have the localization in this case. Okay. So just to I still have a few minutes left. I will just tell you how you choose the super operator T, for example, the interaction operator. Because I already said P is done, Hamiltonian is done. Let's come to the operator T. So the super operator is something that acts on an operator and gives you again another operator. So for example, the way we have the way you define the matrix element of a super operator, it is like this. For example, let's say if T is such an super operator, it acts on A and gives you B. So then this is the matrix element of T where you have 4 indices. So all you need to specify is what is the matrix element of the operator T. Okay. And for the projective measurement case, what you want that you want your density operator to evolve like this, because I'm talking about the projected state, not the leftover state. And from here, you can write what is the form of the matrix element of this operator T here, and then you know what to do. You do this simple algebra here, and you find what you get. So, and for the resetting case, so here again, so if you see that this would be your density operator before the interaction, and then the action of T is such that you get the projection operator here. So density operator is like this, and when you know this, you know what are the matrix element of your T operator, and then you do all of this thing and you find the solution. Here in the resetting case, you find a nice renewal form. So you see, J square was the original propagator in the tight binding case, and the first term here, it tells you, okay, there were no resetting, but the second term, this tells you, okay, you had a resetting, I mean, at a last time of inset, because when you have resetting, the only thing matters that when was the last reset. So suppose you have the last reset here at this point, and then from here there were no resets, so that's why you have this J square here. You have a resetting that comes from this this lambda and exponential lambda T. These factors, they take care of the effect that you have a last reset at time, at this point of time, and after that you didn't have any reset. So this type of like renewal form, so you will see like whenever you have this exponential resetting also in classical systems. And for example, this is the classical part, and in this paper you will see the quantum part. Okay, I think I don't have any times left, so just to conclusion. So what we show you, we show a general framework that how you can do some analytical exact calculation when you consider non-unitary interactions. So we show, like we apply the framework for the tight binding model. So for TBM and projective measurements, we show that there is this freezing of the system in initial state, and we show like akin to Zeno effect when you have stochastic resets, so you have localization. So this is for another problem where we also consider a time-dependent Hamiltonian, and again you see localization, but today I didn't tell you about this. So what we see that this classical and quantum interplay, so it leads you to from coherence to decoherence, because if you have delocalization before, because of stochastic reset, now you have localization. And in like for future direction, you can also do some unitary evolution, continuous monitoring, or many body quantum systems, something like that. And thank you. So these are the references. And if you have any question, I would be happy to answer.
Okay, so let's thank the speaker first.
Thanks for the very nice talk. I didn't understand a thing. At the beginning, you said that in the first scheme you proposed, you made a measurement on the initial position. Is it some kind of like post-selection? So you measure the position and you only go on if the position is measured in the first site? Or can you explain a little bit?
No, it's not something like, it's not like that. So it's like you have to choose a projection operator, right? So you can choose to project to the initial state, or you can also choose to project to another state. So it is completely possible. So in my example, I chose to the initial state, but you can do whatever you want.
So it's like either the initial state, the POVM is like either the initial state or everywhere else?
Yes,
okay.
Yes, you can choose. It's completely general. You can even choose like multiple sites to project.
Hello? Okay.
Yes.
Thanks. I'm just wondering, so you've chosen like a Poissonian probability for the reset because it's like an exponential way to, and then you choose some reset. So I'm just wondering why you choose to model the evolution as this kind of semi-Markov process on the master equation instead of, for example, just introducing a rank 1 jump operator to your Lindblad equation and just using a standard Lindblad.
So what I would say that, see, this, okay, yeah. So when you come here, So this is completely general, right? So I want to express the power of this like formalism. So when you are here, you can choose, you are free to choose anything. You are free to choose any distribution between the time gaps. You are free to choose your system, Hamiltonian. You are free to choose your interaction operator. So I chose the exponential time gaps here just because the further calculation becomes simpler. But this is completely general. Okay, so you can choose and you can apply.
Thank you. Thank you for the talk. So I have a doubt because you said at some point that in the first case with the projections, you have some leakage of probability.
Yep.
So are not updating your state like according to the outcome of the measurement?
For example, let's say here. So you see, I start from the initial state, I let the system evolve, and then I project it here, right? So that's why I'm not considering my further evolution is starting from this point. Okay. Now, if you see the site of occupation probability or the survival probability, you will see it will decay because some part of the wave function it is lost. So when you project, so there are two parts: projected part and what is left after the projection. Since I am considering only the projected part here, so you will always have this leakage. So that's why the survival probability will always decay as a function of time.
Okay. But I mean, you can also like update the state of your system once you project, right? So yeah, in that case, you will not lose probability, no? So if you you get the part that is that you obtain from the measurement, from the projection, and then in general, what you do is okay. Then I see my particle is here, and then so I normalize my.
Yes, exactly. If you do that thing, what you will get? So you will get this leftover case that Abhishek has, like they have worked on this thing. I can explain it to you on a blackboard.
Thank you.
If you do that, you will get that case.
Thank you very much.
Any other questions? If not, then let's thank the speaker and we move on to the next part.
Thank you.